At 18:38 hours, a Ukrainian HIMARS launcher was deploying into its designated firing position on a dirt road 4 kilometers south of the northern Kharkiv border sector. It carried a single pod of 6 M31, two guided rockets aimed at a target roughly 74 kilometers northeast. The operators knew this launch site well. They had calculated the margins. At maximum guided rocket range 70 kilometers in, change every single kilometer between the Sprefers launcher and the Belgorod energy complex was a tactical risk they could not afford. Inside the city, the Luch power station operated at nominal baseline capacity. Its twin General Electric turbines were pumping out 60 megawatts of electricity and 62.4 gigacalories per hour of thermal energy into an urban grid serving tens of thousands of citizens. The facility operators anticipated no imminent threats. Look south. They assumed total energy security. In modern warfare, that grid became a target coordinate, where strategic defense collapsed. The HIMARS is not traditional field artillery. It operates on precision doctrine. Think of it as mobile strike delivery on a 5-ton medium truck chassis. 1 crew, 1 pod, 6 lethal missiles. Firepower. A battery can hold execute a salvo within 60 seconds and displace instantly before the final rocket clears flight. This shoot-and-scoot tactic is no luxury. It is the fundamental law of survival. Because the instant rocket ignition occurs, hostile counter-battery radars begin to track the trajectory back to the source instantly, calculating the exact origin. The M31 unitary warhead, our target loaded that evening, is precise. Variant. Our satellite-aided inertial guidance locks the coordinates before launch. Once launched, we have no correction window. No operator steering, no second chance. The warhead either strikes the programmed coordinate or it fails. These guided rockets do not saturate areas. They do not scatter submunitions across a grid square. They concentrate 200 pounds of explosives on a single coordinate. Our entire tactical equation depends on that single coordinate being absolutely correct. For the Ukrainian artillery crew in the cab of their launcher, those final minutes before ignition were strictly procedural and silent. Target coordinates confirmed against our latest imagery. Elevation. Data verified. Weather. Corrections processed. Wind aloft air. Pressure, temperature gradients along the bridge. Flight path fed into fire control. Computers. The pod was indexed. The vehicle oriented the diesel, the engine already idling. Range is the critical variable that compresses everything. Standard guided rockets are rated at 70 kilometers and beyond, but the Belgorod target sat at roughly 74 kilometers from the closest launch point along the Kharkiv axis. That left a margin under 6%. Not a deep strike, nor a shot lobbed from safety behind our lines. This was a strike launched to the absolute edge of what the weapon could comfortably promise were atmospheric conditions. Propellant heat and guidance. Drift dictate success. We had almost zero margin in reserve. Confirm target. No guidance correction after release. At 6:41, the first rocket clears the pod. A violent column of white exhaust punches into the dusk, then a second follows, then a third. Our driver is already shifting gears before the pod completely empties. A guided rocket, powered flight, crosses its entire range in roughly 90 seconds. There is no loitering, no mid-course corrections. The internal guidance computer calculates the trajectory at ignition, climb arc, descent, and the weapon follows a one-way trajectory that cannot be recalled, corrected, or aborted. Once the motor burns out, that round is a guided projectile, traveling at supersonic projectile speed toward a target coordinate locked in before launch. For our crews on the ground that launch, signature is their most vulnerable moment. At 74 kilometers out, they were dangerously close to hostile territory where Russian in-ground sensors along the Belgorod network would acquire the plume within seconds. Every second that launcher remains motionless after firing is a second closer to counter-battery fire landing on their heads. The launcher veered south and accelerated. Cab blacked out headlights. Off. Behind it, the missiles are already climbing through 4,000 meters, punching through the atmospheric inversion layer, where freezing air meets the warmer zone above. At 6:42, the rocket engines run dry. The boost phase, the loudest, hottest, most detectable portion of flight, lasts only seconds. Once those motors burn out, the guided rounds transition to purely ballistic, fast cooling, arcing past 15,000 meters before tipping into descent. The onboard guidance inside each rocket, our GPS receivers were still functioning, cross-checking against the inertial platform, calculating micro-corrections for the control surfaces designed to steer our warhead onto its final path. But these adjustments were marginal. Our primary ballistic flight path was set at launch. The missiles were committed. Across that hostile border arc, Russian monitoring systems logged the incoming strike. Our guided rocket, during ignition, is impossible to hide. The booster engine radiates massive thermal energy, lighting up enemy infrared space sensors instantly within visual range. Furthermore, the radar signature of supersonic weapons climbing through open sky is massive. Detection was guaranteed, but tracking does not mean interception. To shoot down our rocket in flight, defenses must lock onto the threat. After booster burnout, when the thermal signature FAD, reacquire target tracking via radar, calculate a fire control solution against a warhead flying at extreme supersonic speed on a descending trajectory, then launch a countermissile with sufficient energy to reach the required altitude before the incoming threat drops too low to hit. We calculate this engagement window in mere tens of seconds, rapidly shrinking. Our intel shows no enemy air defenses along the Belgorod perimeter engaged out salvos that night. Whether they missed the detection entirely, hesitated to fire, or simply failed to intercept our battle damage assessment is technically inconclusive, but our sensors confirmed the final impact. 90 seconds. That was their entire window, from when the hostile rockets launched to when the terminal math arrived. Impact. 74 kilometers northeast, the priority target was operating at maximum capacity since DOM. The Luch facility was engineered specifically to plug a critical vulnerability in the local Pracer's 5 network. 2 LM2500. High-output gas turbines, industrial-grade power plants adapted from naval propulsion designs, each built to run alone, generating critical power and vital heat for southern Belgorod. We identified 3 critical integration points within the municipal network. First, high-pressure lines feeding fuel directly to the turbines. Second, 110 kilovolt lines distributing electricity to the grid. And third, thermal mains carrying steam straight into the civilian sectors. From our tactical perspective, this footprint, the core of its efficiency, was exactly what made it vulnerable. In theory, it hardened their defenses, securing the regional grid. Dual redundant units, multi-role output, one centralized footprint doing what normally demands 2 separate sit. That was peacetime doctrine. But strategic planners made one error, assuming immunity from strike. A standard legacy power station stands structurally isolated. Eliminate it, and power simply bypasses. The damage. Tactical damage is localized. The recovery is predictable. But a combined energy station is not isolated. It is a node. Power, thermal, and gas. Networks converge in one tactical zone. Damaging the primary generators doesn't just cut grid capacity. It snaps the thermal loop that pumps heating to civilian sectors. It cuts the fuel lines that spin the turbines. This triggers a cascading failure down all connected lines simultaneously. Because these pathways were designed to rely on each other, it was built to secure Belgorod. That night, it became the exact point of systemic failure. The first payload struck at 1843 local time. The terminal phase of a guided rocket dive is nearly vertical. The warhead plunges through the final 1,000 meters. Guided by continuous GPS and inertial, Calculations made fractions of a second before impact. There is no warning whistle. At supersonic speed, the sound trails the impact. The rocket's 200-pound high-explosive payload detonated inside the central thermal facility and the adjacent distribution assets. A unitary warhead does not scatter shrapnel widely. It focuses maximum kinetic force on target. Against a reinforced military bunker, that blast is meant to penetrate concrete and steel. Against civilian power infrastructure, like transformers and switches, unshielded overhead lines and turbine housings, critical control nodes protected by nothing sturdier than sheet metal and simple chain link fencing. Strike density was catastrophic. A secondary strike followed within seconds. Governor Vyacheslav Gladkov would later confirm 2 coordinated strikes utilizing a total of 6 warheads targeting the regional capital that night. If all 6 struck the complex, or targeted multiple separate infrastructure nodes across the sector, remained unclear. At 6:44, the city failed. The grid failure was not instantaneous. It cascaded. First, the municipal streetlights. Entire arteries lost illumination within seconds of terminal impact. Lamps sputtered once and failed as the primary supply line cut out. Next, traffic controls. Intersections went dark across southern sectors. Vehicles stalling at dead junctions with no clear indication of right-of-way. Then civilian living sectors, apartment blocks went dark floor by floor as vulnerable portions of the grid shed load or auto-tripped under system fault. Protection. Transit shafts seized instantly, trapping non-combatants inside pitch-black steel boxes with zero communication. Next, thermal failure. The cogeneration facility did more than generate power. It pumped hot water into the city's district heating mains, where critical thermal energy flows from the plant through a pressurized pipeline network directly into radiators and taps across southern sectors. When the plant's generation collapsed, the entire thermal circuit began to fail. The critical thermal conduits lost pressure. Thermal supply to the residential sectors slowed, then failed. In an urban theater where temperatures were already dropping towards single digits, this complete loss of heating after dark was no simple inconvenience. It signaled the phase of secondary network collapse, cascading, demanding far more time to restore than simple grid repair. System engineers fought the crisis from consoles that retained operational power, executing emergency load transfers, drawing power from neighboring sectors, along surviving perimeter lines, spinning up auxiliary generators at critical zones and defense sectors. They scrambled to isolate compromised nodes, preventing systemic collapse from propagating deeper into the regional distribution network. But network redirection has limits. When the compromised target is no mere peripheral node, but the core generation and distribution hub handling both electrical and thermal output, there is no operational bypass. Surrounding tactical assets were never scaled to handle 60 megawatts of load. The entire network relied on Luch. Without it, the system had to improvise using unrated hardware, never intended for this combat load. Bypass where possible, defend where you cannot. By 7:30, network failure expanded beyond urban parameters. Surrounding sectors reported immediate systemic grid failures. Command confirmed the strikes, catastrophic subsystem damage, severed lines of power and water, with multiple regional casualties reported. Engineering units worked through the night. Critical facilities switched to emergency auxiliary power within hours. But total recovery of the grid took far longer. Then came the strategic consequence that operators in the bunker could not calculate in advance. Gladkov himself warned the power loss would cripple the tactical missile and drone early warning networks. The sirens, the warning broadcasts, the integrated networks advising civilian populations to take cover. Without power, the early warning system fails. This kinetic strike did not just degrade systems. It stripped Belgorod's capability to shield its population from subsequent incoming salvos. If we analyze the attack geometry, the target was not chosen for its high cost. It was selected purely for its high integration, embedded into municipal power heat and water infrastructure so deeply that failure of one disabled all three. Proof of impact was not the blast, but dark. 6 rockets, 1 battery, 90 seconds of flight time, against a critical node taking 20 years to build, destroyed in 10. That engagement was not the end. The municipal power grid was hit again weeks later. And again, and again. The sector did not fail because defensive batteries were saturated by volume. It collapsed because several precision munitions struck the single point where power, heat, and civil defense converged. The architecture engineered to protect the city became the absolute epicenter of total defense collapse. Deep in the northern Kharkiv corridor, we mapped our next battery position. The reconnaissance is done. The target package is already locked. The command grid flickered back online. Yet our tactical vulnerability remains exposed.